Hi guys, today we start week 6 for topic 2.
Topic 2. Flow of water through soil.
Program outcomes PO1, PO2. Our course outcomes CO1, CO2, and COPO mapping CO1, PO1, CO2, PO2. This is our learning outcome. At the end of the lecture, students should be able to determine the coefficient of permeability K for field permeability test by using confined aquifer and unconfined aquifer. Field permeability tests. The main problem associated with the laboratory tests are: first is soil sample. Size taken is quite small, unlikely to be satisfactorily representative, meaning that the soil sample is not really representative of the real soil condition. Number 2, reliability of lab measurement. It may, because of the lab errors, presence of air bubbles, variation in density and porosity, and also maybe variation in temperature. Number 3, reproduction of field condition. Very hard to obtain truly undisturbed sample, variation in flow direction, pore pressure, and also effective stress condition. For field permeability tests, we are conducting steady state pumping tests. We have two types of tests. First, pumping test in a confined aquifer. Second, pumping test in an unconfined aquifer. What is aquifer? Aquifer is an underground formation or permeable rock or loose material which can produce useful quantities of water when accessed by a well. This is an example of pumping tests in the field. For the pumping test, we're pumping out the water. Assumption made in estimating the permeability. First, the soil mass is homogeneous, isotropic, and infinite size. Second, Darcy law is valid. Number 3, flow is radial toward the well. Number 4, the hydraulic gradient at any point in the water-bearing stratum is constant. Number 5, the pumping well and observation well are fully penetrating in the soil. First, we go for the pumping test in a confined aquifer. So what is the confined means? The confined means that something in closed space. Confined layer of impermeable material, rock or clay are both above and below the aquifer. So means that this is impermeable at the bottom and then we have impermeable layer at the top. The upper layer of impermeable material that limit groundwater movement into the confined aquifer. By referring to this figure, you will see that this one is horizontal flow from left to right. Alright, and then this is the pumping well. The pumping well is used to pumping out the water. The discharge of water is known as Q. And then you will see here, this one is the initial groundwater table. And then you will see here, this is the observation well 1 and observation well number 2. And then you will see that after you pumping out the water, the initial groundwater table here draw down to the new groundwater table. Alright, this is first drawdown for observation well 1. This is second drawdown for observation well number 2. Alright guys, look at this. This is R1. R1 is the radial distance from the pumping well to observation well number 1. This is R2, the radial distance from pumping well to observation well number 2. And then look at this, we have the H1, the height for the observation well from the impermeable layer at the bottom to the new groundwater table after drawdown. H2 is the height of the groundwater table after drawdown from impermeable layer to the new groundwater table. And then you have the D, depth of aquifer. Okay, look at this. This is derivational formula. In a steady state condition, the flow is considered through an elemental cylinder having radius r, thickness dr, and height h. So hydraulic gradient outside to inside, I is equal to dh over dr. Area through which flow takes place, A is equal to 2 pi rd. Starting with the Darcy equation, Q is equal to AKI, so A is 2 pi rd times K times dH over dr. Look at this. This is Ki. This is I. So dr over r is equal to 2 pi Q times dk dH. Integrating ln r2 over r1 is equal to 2 pi dk over q times h2 minus h1, giving k is equal to q over 2 pi d ln r2 over r1 divided by h2 minus h1. Q is the discharge, D is the depth of aquifer, R1 and R2 is radial distance, H2 and H1 is the height. You may use this equation K 2.3Q over 2 pi D log 10 times R2 over R1 divided by H2 minus H1. Right? This is all the symbols means. Q for rate of pumping, R1 distance pumping well to observation well 1, R2 distance of pumping well to the observation well 2, D is thickness of the aquifer, H1 the observed water level in observation well 1, H2 is the observed water level in the observation well 2, D is the drawdown. Example 1. Figure shows a pumping test conducted on a 5-meter layer of well, graded silty sand sandwiched by 3 meters of soft clay at the top and by impervious granite underneath. The pumping well was sunk in the layer of sand just above the impervious granite stratum. 2 observation wells were located at 20 meter and 65 meter from the center of the pumping well. This is R1 and R2, where the drawdown observed at 1.75 meter and 0.89 meter respectively. The quantity of water collected was 4,500 liters per day, and the groundwater table was 1.52 meters below the ground surface. Determine the coefficient of permeability K of the soil. Alright, how to calculate? Look at the next slide. Alright guys, from the statement in the example 1, look at the figure here. Okay, so from the statement, the radial distance R1 is 20 meter from the observation well 1 to the pumping well, right? From the pumping well to observation well, radial distance is 20. And then you have radial distance 2 from pumping well to observation well 2, 65 meter. And then the statement stated that you have 3 meter thickness of clay at the top, and then you have the aquifer 5 meter, and then the distance from the surface to the groundwater table, the initial groundwater table, is 1.2 meter, and then the drawdown first is 1.75, and then drawdown 2 0.89. So what you are going to do is you have to determine the value of H1 and H2. So H1 is the distance from the impermeable layer at the bottom to the drawdown for the observation well 1. So means that H1 is equal to 5 plus 3. So 5 plus 3 minus 1.2 minus 1.75. So you will get H1. H2 is 5 plus 3 minus 1.2 minus 0.89. So that one is H2. So this is the solution for H naught. 5 plus 3 minus 1.2 is 6.8 meter. H1 is 6.8 minus 1.75. Okay, this is the answer. H2 6.8 minus 0.8. This is the answer. So how to determine the value of K? So first you have to convert a Q from 4,500 liter per day to meter cube per second. So this is how to determine the Q value. And then K is equal to Q ln R2 over R1 divided by 2 pi D times H2 minus H1. So what is the final answer? This is example 2. Alright, so figure 5.8 show the arrangement of the pumping well and observation well together with relevant dimension. Initially, the prismatic surface was located at depth 2.5 meter when a steady state was achieved at a pumping rate of 37.4 meter cube per hour. The following drawdown were observed. For pumping well, the drawdown is 4.46 here from this point initial water table to the new water table. And then for observation well 1, D1 is 1.15. So the distance from the initial groundwater table to the new drawdown 1.5, and D2 is 0.42. And then you have the radial distance 1, R1 is 15, and the radial distance 2, 50 meter, and then you have D 11.7 meter, and then you have the Q 37.4 meter cube per hour. So first is calculate the value for coefficient permeability of the sand using observation well data, and then number 2 is corrected drawdown level in the pumping well. And then the last one, estimate the radius of influence at this pumping rate. So first, observation well data, R1 is equal to 15, R2 is 50 meter, H0 is 11.7 plus 7.4 minus 2.5 is 16.6. So H1 is 16.6 minus 1.15. Okay, this is the answer. And then H2 16.6 minus 0.42. So this is the answer, 16.18 meter. So Q is you have to convert from meter cube per hour to meter cube per second. 37.4 divided by 3,600. So you will get this answer for Q. The D is 11.7. So K is 2.3 Q log 10 times R2 over R1 divided by 2 pi D times H2 over minus H1, or you also can use another equation which is using a ln. Alright, so this is the final answer, 2.33 times 10 power of minus 4 meter per second. Calculation for radius of influence or R0. No drawdown, then put in R2 is equal to 50 meter and H2 16.15 meter. So K is equal to Q times log 10 times R0 over R2 divided by 2.727 H times H0 minus H2. So final R0 is equal to 100. Pumping test in an unconfined aquifer where where the groundwater is in direct contact with the aquifer. Alright, so how we know that one is for confined and unconfined? So for unconfined, you have the impermeable layer at the bottom, and then you don't have impermeable layer at the top. Alright, so look at this. This first is pumping well here. First is pumping well here. Second is observation well 1, observation well 2. So first is radial distance is distance from pumping well to observation well 1. Radial 2 is distance from pumping well to observation well 2. So you have R1 and H2. For this one, we don't have D, but we have H1 and H2. Similar with the confined, H1 is the distance from impermeable layer to the drawdown for observation well 1. Okay, for H2, the distance from impermeable layer to the drawdown for observation well 2. Alright, and then you look at this. For the pumping well, we have the Q value. Q is discharge value in meter cube per second. Alright guys, look at this. You have the groundwater level, and then this is original groundwater table. You have the observation well, you have 2, you have pumping well, and you have drawdown groundwater level. Alright guys, this is the derivation of formula. Under condition of steady state pumping, the hydraulic gradient at the given radius is assumed to be constant in a homogeneous medium. Consider an inflow through an elemental cylinder having radius and thickness and height. So this is hydraulic gradient outside to inside. I is equal to dH over dr. A is 2 pi RH. Q is AKI. So means that you just put all the information. 2 pi RH times KI. This one is K, this is I. dH over dr. So dH over dr is equal to 2 pi over Q times KH dH. So this is integrating. The final answer, you will get K is equal to Q ln R2 over R1 divided by pi times H2 squared minus H1 squared. Or maybe you may use this equation also. Alright, so this is the definition for K, Q, R1, R2, H1, H2, and drawdown. This is another example. You may refer here. We have the pumping well, observation well 1, and observation well 2. The water table is located at depth 2.5 meter. And then the pumping rate is 23.4 meter cube per hour. So you have to calculate the value of coefficient permeability of sand. Actually, this one is very simple. Alright guys, look at this diagram. When you look at this diagram, you will see that this one is impermeable layer. At the top is no impermeable layer. This is permeable. So what we can do is, first is you have to decide whether this one is confined or unconfined. So of course for this one is unconfined aquifer. Alright, so first what you do is you have to know the value of groundwater table, the initial groundwater table from the surface to the initial groundwater table, the height, and then this is the pumping well value, discharge, and then you have the radial distance here from the pumping well to observation well number 1, this is R1, and then pumping well to observation well number 2, this one is R2, and then the value of H1 from the impermeable layer to the observation well number 1. Okay, drawdown. You have to minus with the drawdown and also initial groundwater table, and then the value of H2. Alright, so from all of this information, you may calculate or determine the value of coefficient of permeability K. Alright, this is the solution. R1 is 18 meter, R2 is 62 meter. So H naught is 12 minus 2.5, which is this one is initial groundwater table. So you will get the initial H naught is 9.5. So H1 is 9.5 minus draw down 0.96, which is that 8.54. H2 9.5 minus draw down number 2 0.48, so you will get 9.02 meter. So Q is 23.4, so divided by 3600 to get meter cube per second. Alright, so you have to convert the Q value to meter cube per second because this is in the unit SI meter. Alright, so K is equal to Q ln R2 over R1 divided by pi times H2 minus H1. Alright, so is equal to 3.04 times 10 power of minus 4 meter per second. 7 rules of life. First is smile. Number 2, be kind. Number 3, don't give up. Number 4, don't compare. Number 5, avoid negativity. Number 6, make peace with your past. Number 7, take care of your body and mind. Thank you guys.